So yesterday, what we did was to basically derive the formulation of the equation of motion, of Newton-Euler's equations of motion for the case of generalized parameters which are all independent. So basically, no constraints are enforced. So to recap it, so we have, of course, the case of MB rigid bodies. And we saw that in the case of no constraints enforced, we have this equation. Okay, a very simple one, where M is the mass matrix of the system. And Q is basically a combination of the external force, of the resultant of external forces generalized, okay, so defined with respect to the generalized parameters, and the quadratic velocity vector, which basically takes into account inertial effects and Coriolis effects, centrifugal forces, and so on. So this is a very basic case, and in fact, you can somehow look at this equation and see basically a very similar formulation to that of the Newton's second law. Of dynamics. No? Something like this. In fact, that's part of the reason for which we call these equations Newton-Euler's equation, because this first equation, which in this case is the only one, is ascribable to Newton. We will see at the end of today's lesson that there is a reformulation possible for this equation of motion, which will, through which we will be able to identify two equations, one for the translation, the other one for the rotations. The former is ascribable to Newton, the latter is ascribable to Euler, and then from these Newton-Euler's equations. But this is just a matter of formalism, if you want. So, this being said, now what we have to do is to consider the case of constraints being enforced, and in particular, we will enforce, as we did last time, holonomic constraints. Okay, only holonomic ones. Now, what we do, if you remember, in this case, is to go a step back and start from the D'Alembert-Lagrange formulation of the equations of motion. Okay, so we basically start from here. Like so. Oops, sorry. Okay, that's usually where we start from. Then what we do is to take advantage of the fact that we are dealing with holonomic constraints, and therefore we can do the following partition. So From the constraint, if you remember, we had vector of generalized coordinates, which can be partitioned into independent and dependent ones, and this can be always done. But then we can also do the following, if you remember, right? So basically, we can express the vector of generalized coordinates, all of it. We do a partition, and then we basically say that, of course, the first part is just identical to itself, and then the relation between the dependent and independent is through this one, with, if you remember, just for the sake of clarity, being equal to minus c qd to the minus 1 c qi. So that's what we do, and that's the simplest and the most favorable case that we can deal with. So what we have to do is just basically substitute this. And so what we get is the following. So M yeah, so we can call this this is a matrix, of course, no? We can call this matrix as B di, okay? So just for the sake of clarity of notation. And so we basically said this is MB di Qi double dot minus Q, all of this being transposed, and then again right. So basically what we did was to do nothing else that's a substitution, and as you can see now, we were able to rewrite everything just in terms of the independent coordinates. So very simple. Now, since everything here is written in terms of independent coordinates, we can pass from the D'Alembert-Lagrange formulation to the Lagrange equation. And so we can basically say that since all of this is 0, then all the components of this equation must be 0. All the addendum of this sum must be 0. Right? And so basically we pass from here, from this one to this one here. Double dot, like so. Now, typically, we prefer to deal with a mass matrix, because you see now, this is a n times n matrix, right? That's the mass matrix, because it encompasses everything, right? So this is an n times 1. So this one instead is an n times ni, where ni is the number, again, of independent coordinates, and this is ni times 1. While this is, of course, an n times 1 vector. All right? So what we want to do, and what is typically done, is to basically pre-multiply this equation here by BDI transposed. Okay? Of course, we have to pre-multiply both of the terms. So pre-multiply by B di transposed. And what we get is the following. Very straightforward. And from here, we basically redefine this as a new mass matrix, but this time of the dimension ni times ni. This we can call it BDI if you want. MDI, sorry, which is an Ni times Ni. And then we redefine this one here as Q di. Okay. So that eventually we just get the same very simple form of the expression we had before. But this time only, taking into account a much smaller problem. So this is formally basically identical to what we have seen before, but please, you have to take into account that here, while the dimension of this one here, this one that we have already seen, is an n times n, so this is an n times n, just let's write it. So n times n. Here in the other case, we are with an equation which is Ni times Ni, at least for the mass matrix. Then, in fact, this is a vectorial equation, so it's Ni times 1, if you want. But this means that if you eventually have a number of equations which is, for example, equal to the number of generalized coordinates minus 1, as we have seen, for example, for the Poiseuille mechanism, this could be a scalar equation. So your system, even of, composed of many Lagrangian parameters, can be reduced, like in this way, in this case, to a scalar equation in the simplest case. So you see, embedding the constraints equation into your equation of motion is really powerful. It's very convenient. Unfortunately, it cannot be done all the time. Okay. In fact, this is what we're going to see right now. So for the case of non-holonomic constraints, so I'm not sure what is the numbering that we adopted. Yeah, 2.1, so 2.2 in this case. 2.2. So 2.2 non-holonomic constraints. Okay. Yeah.
Just to clarify the final point,
Mm-hmm.
Poiseuille mechanism, it will convert into a scalar because there is only one independent.
Mm-hmm. Yeah. As I said, you see here, this formalism is only written in terms of degrees of freedom. It's really actually quite useful if you get used to call in the independent Lagrange parameters degrees of freedom, because they are day code. Okay, so the degrees of freedom here is what constitute the basis onto which we write this formalism. So if we only have one degree of freedom, that's a scalar. Okay, it's a scalar equation. All right, so non-holonomic constraints. Well, in this case, again, we reintroduce the work of contact forces as QC times delta Q, right? And this is typically equal to 0 because we always make the assumption of workless constraints, no? All right. But then, as we did before, what we do is basically writing down this QC, so the generalized contact forces, as minus CQI. If you want minus CQ, transpose, apply over the Lagrangian multiplier lambda. Okay. So this is here the Lagrangian multiplier. And these are, again, contact forces. Contact forces. So, once again, please be aware of the fact, and keep in mind that the fact that the co-strains are workless doesn't mean that you don't have contact forces. You do. The fact is that typically they are expressed in such a way that they don't contribute in any way to the virtual work. Okay. So we again, enforce the partition. So that basically we have that Q is equal to Qi transposed, and then we have the dependent ones. And so this basically allows us to write the following. Yeah, of course. Yeah, let's go like this. Okay. So what did I do here is basically just rewrite this equation here. That we have already written. What is it? Oh, yeah. It's this one. The D'Alembert-Lagrange equation. And then I've done a partition between dependent and independent. And this basically also have partition of this part here, including, in this case, contact forces, as we have done for the augmented formulation, if you remember. So basically, if you want, you have that our M, as long as you do, actually, let's write it here correctly. Since you do this, also your matrix gets split into 4, no? MII, MID, and then we have MDI, and MDD. Okay, it's just basically a partition which follows from the partition of the generalized coordinates. And then again, I've also split, the vector of generalized vector forces. So I can also write it here if you want. Q is basically done as qi and qd. Okay. And also, of course, the vector of contact forces has been split into two. All right. So this one, then this follows, and from always from this one, this follows. This is the vector of generalized forces, external forces, and then also the contact forces. So I and D from here, basically. Yeah, sure, no problem. Let's actually write it properly. Where? So from here, this follows, right? From this, you have that our M gets split into 4, no? Which is M I, M I D, M D I, and M D D. Okay? As long as it is applied to this one, all right? For the same reason, we have the vector of external forces plus the vector of the quadratic velocity vector gets split into 2. So you have Qi and Qd. Okay? And for the same exact reason, you have the Qc, the contact forces, are split into 2, which are this one here. Okay, so you have minus CQ, let's say I, times lambda. And then you have minus CQD applied over lambda. Okay? And this is what you get, you see, in here and in here. Of course, with the minus sign, okay, in front. Mm-hmm. No, no, perché il CQI, questo qui, ha dimensioni sostanzialmente, allora, un attimo, allora. Sì, è giusto. Sì, è giusto, però... No, perché questo qui ha, siccome questo è so since this one is transposed, this is ni times n. Okay, so this has to be n times 1. All right, so that eventually you get ni times 1. Okay. So this is correct. Okay. So why did we do this? We did this basically so that, again, we choose, and that's why it cannot be split, you see now, so that basically the first component here, okay, no, sorry, the second component here is 0, okay? That's why you see all of this, which is between brackets, we chose lambda so that it is 0. And that's why it has to be the same lambda here and here, so we can do the partition. It wouldn't have sense, that's why. Okay. Yeah, so Let me just see if I wrote it this way. Yeah, yeah. Okay. Since this is 0, I'm left with what? Well, with the rest, with the following part, no? What is left is this one. It's just very similar to what we have done for the particle case, no? The system of particles. Here we have bodies, but the reasoning is just the same. So again, since the Qi are independent, I can basically put all of this equal to 0, okay? So again, the equivalence of this scalar equation equal to 0 can imply identically a vector equation. So again, yeah. I'm rewriting all of this because now let's take a look of one fact. So this is one, okay. But then again, we also take the previous one, okay, the one which we ensure to be 0 resorting to the Lagrange multiplier, which is this one. Okay, so we can rewrite all of this. We can basically reverse the partition. And so we basically get the following. Yeah, let's write it like this. And of course, what? The constraints equation, Q dot and time. Okay, because of course, here I cannot embed my constraints equation into the formulation. I have to always take them into account. So this is a mixed, again, differential algebraic system, very difficult to solve. In fact, what we do typically, since it is preferable to write all of the equation of your system in the same way, namely differential one, because it would be nice to be able to always be capable to write differential equation into algebraic equation. And this is somehow actually possible through, for example, the Laplace transform, no? Or Fourier transform. This is what you do. But in this case, what you do is actually turning everything into a differential equation. How do you do that? Well, basically, somehow adopting the same line of reasoning that we have seen for Keynes' equation. So what we do is the following. So we try to write the former system in terms of differential equations only. To do that, what we do? Well, basically, these are the differential equations. These are the algebraic equations. Okay, the algebraic equations are the one which enforce the constraints. So we basically turn the constraints equation from algebraic to differential. So we turn the constraints equations from algebraic So what is it that we do? We basically just differentiate. So we see that basically this is the form, the general form that we know. And we saw that basically this could be written through a differentiation, like so. No? Through a derivation with respect to time. This is what we have already done. But what we do is to basically differentiate one more time. If you want, we derive with respect to time one more time. And we get the following. We're going to do this times the q over the t plus the cq over dt. And all of this is multiplied by cq. No? This is the chain rule, basically. And then we have cq like dq dot over dt. And then we have the ct over the t. And this is again equal. We can rewrite it basically as CQQ, and this is basically CQQ. It's this one, it's this term here. Times Q dot squared plus 2 times CQ and derive with respect to time, which is this one here. Okay. Times Q. And then we have CTT, which is this one here. And of course, we have C, Q double dot equal to 0. Okay? Now, we take all of this, and we just basically rewrite the following. C, Q double dot equal to minus C, Q plus 2 times C, Q T times Q dot plus C, T, T. And this we call QS, okay, by definition. Why did we do all of this? Because now we can rewrite the original system as follows. The mass matrix CQ transposed CQ 0. So our new vector is this one here. Okay, you see now it's a total differential system. No more algebraic equations. Why is this done like this? Because you can solve this through the inversion of this. That's why you put it in a form such that you have to invert this matrix, apply to this one, and you get your solution. Okay. So we basically had a new form that allows us to resolve, basically, to solve the system through basically a matrix inversion at the cost of what? Of transforming algebraic equation into differential ones, which is not always a desirable thing to do because you increase the level of complexity of the system. And this is actually how your codes work. Why? Because basically this is a formulation that can deal with all kind of constraints. And this is actually how Adams works. Okay? Because Adams is a software that, as you will see, it is basically capable to deal with rigid bodies. But then there is an addendum, if you want, like an additional part of the system which allows you to include also the effect of deformability. But if you exclude for a moment this capability, this is how it works. It works just like this. And in fact, in the seminar that actually the first one, I think it's the 7th of April or so, Mr. Catalani from MSc will explain you how to deal with a system. Basically, it's a satellite, and to study its dynamics, for example, for the deployment of the solar panels, only taking into account rigid body motion. Okay, so no effect of deformability at first, And this is actually how you're going to solve it, not you. Luckily for you, but the code will do it for you like this. Okay. All right, now let's try to do one last passage, which is, I don't know, more of a formalism-like, because it's, something that is meant for you, not to give you any more insight on this, but because you could find, this equation to be written in a different form. Okay, if you're not careful enough, you may, not recognize them, but they are just basically the same. So this is for me, the main form in which you should know, you should be aware of these equations, because this is how the codes are also written. But I don't know, for those of you who will be interested, I don't know, in pursuing some, I don't know, a research career or whatever, you should be aware that this is not the only one that exists. So now you will be introduced for probably half an hour in the derivation of the canonical forms, the so-called canonical form of Newton-Euler's equation. And as I was mentioning in the beginning of the lecture, these explain a little bit why they are called Newton-Euler's, because you're going to see basically two equations, one ascribable to Newton, the other one to Euler, and this basically tells you about the name. Okay, so it's a little bit heavy in terms of formalism, I know, but I think it's worth it to spend on it half an hour, and then probably forget about it in your future application. But eventually you can say that, okay, once I look at it, I know what this is. So this is, you could call it canonical form. Of Newton-Euler's equation. If you're, I don't know, if you are quick enough, then we can start at least, introducing the effect of deformability as a general, as a general reasoning. Let's see. So, let's see, the kinetic energy, we start from the kinetic energy. For the body I, we know it's like this, where basically we are assuming that we have centered our local frame in the center of mass of the body. So this means that we are doing something like this. Okay, so we basically are missing, so we say body frame centered in center of mass. So we don't have the last term. So we have that Lagrange equation. Becomes as follows. Is the total derivative with respect to time of the partial derivative with respect to the generalized velocities. So here is a little warning if you want. So Qi, this is I know it's a somehow controversial point, but this is not Qi. What does it mean? Here, when I use I as a subscript, this is refers to the number of the body. It's the body I. So it's all of the generalized coordinates of the body number I. This is the independent coordinates. Okay, I know it somehow can be misleading, but I didn't find any any other more clear notation so far. So be aware of that. Huh? But I'm consistent with that throughout all the course and the notation. So you cannot, if you take this, you bear into your mind this one, you won't be confused. I hope. Huh? So let's derive these two terms. Okay, so we have that the Ti over the Qi dot. We have said that already when you derive something with respect to a column vector, you get a row vector. Huh? We have said that already. So what you get is basically this one. R dot I transposed M R R I, and then theta dot I transposed M theta theta I. Okay. Then we apply also the derivative with respect to time. So we have to just, again, do the derivation. So here, as we have said, so the mass matrix, which the submatrix, which is corresponding to translation, is constant one. No, so we don't have any kind of dependence with respect to time. So this is basically what we get. Very easy. Here things are starting to get a little bit more complicated because we know that also the submatrix associated to rotation depends on time. We have seen it yesterday, I guess. So we get the following here. Okay. Now let's rewrite a little bit things, this part here in a more favorable way. So basically, we can write the following. So theta dot I transpose M theta theta dot I, which is the second term that we have written before, can be written as follows. Theta dot I transpose. Then we adopt basically the previously seen expression for M theta theta, which is the following. G I transposed, the one which resorts to the inertia tensor, no, times G plus Yeah, sorry, no, G dot. Okay, so why did I do that? Basically, I distributed this derivation with respect to time over this, once on the first G, and then on the second G, because we know that this is constant, because it's no deformation here occurring. So once here, and then once you have here. But the following holds. GI applied to theta is 0. This is an identity which can be demonstrated. And therefore, I will not demonstrate it, but if you go and check the definition of G and then of theta, you can demonstrate it. Then, of course, G dot theta dot, which is nothing else than the derivative of this. Oh no, there is no dot. Like this. This has to be 0 as well. Okay. And so this is 0, all of the first part. No? See?
Both are varying, shouldn't it be G theta dot plus G dot theta? Because both are varying with respect to time, G and theta.
G and theta what?
Shouldn't it be G theta dot plus G dot theta is equal to?
Yes, yes. But this basically, yeah, you're correct, because here basically we have it's two different yeah, we will make use of this as well. Yeah, thanks. So this basically means that we have that our theta I transposed m theta dot I. This one here, instead, if you recollect it, is by definition omega transposed. Is the definition of omega transposed. Omega was defined like this. So basically, we can rewrite all of the previous as such. Okay. So that just to Okay. Well, I've just basically made the substitution in what was before. So this is the first part of our Lagrange equation. Okay. Then we have the second part. Okay, this part here. And this is the following. 1/2 of the derivative with respect to qi of what? Well, we have basically Ri transposed, MRRI Ri dot, and this is the first part, no? And then we have the second part. Okay. Now you see that here, in the first part, there is no term which there is directly dependent on the q's. So this is function of R dot, not of R. Here, always constant. So this is all the derivative of this first part is 0. What actually applies is on the other side, on the following part. So basically, we can rewrite as follows. We have 0 transposed. Then we have 1/2. Of course, here the only derivative, the only part of the q which matters is the theta. Okay, the only dependence here is not on the r, is on the theta. So I can only as well just keep the derivation with respect to theta. Okay. Of what? Well, okay. Now, since, as I was saying, is 0, as we have said before, it means that also its derivative is 0. All of it is 0. Okay. And this means basically that g I theta dot I is equal to minus gi dot theta I. Okay, from here, this must hold. Okay. So now we're going to make a substitution here. So once again, we have that m theta theta I is omega I transposed theta theta I omega I. No? This you have seen already. So we can write, sorry. So we can write the following. So dt over d qi is equal to the following. Here we have, so not zero, this is 0. It's not theta, it's really 0. And then the second part is 1 over 2 of the derivative with respect to theta I of theta dot I transposed. So here I made a mistake. Yeah. It's like this. Okay. And this is equal to 0 again. Now here you see what we have demonstrated here is that basically I can put my time derivative sign on here, just, I can reverse it just adding one minus in front. So basically, this is what I'm going to do here, okay? So I can write theta I transposed g I transposed with a dot. In theory, I should put a minus in front, but then I'm going to do the same also in here. So that basically no sign is necessary. Why did I do this? Because now, well, the dependence of this expression on the theta is evident, you see? It's here and here. So I can perform this derivation. Let's do it. We are quite there yet, I promise. Okay. But then I do one last thing. Which is reversing again this one. I reverse again the time derivative, okay? So this time I really put a minus in front. But this is omega. Okay, so I can write like so. Okay, so this is this derivation here. No, it's this one here. We will eventually be able to rewrite it in terms of known quantities. I know it was painful, but we did it. Huh? So from where now? So we do again a partition. Partition of external forces. So that basically our Qi is basically just QR I transposed Q theta. Okay. So basically I just divided my external forces in those associated to translation and those associated to rotation. So that we finally can write so now we put together the two, all of our accomplishments, let's say. MRR I Ri double dot is equal to Q R I, and that's the first one. And then we have M theta theta I equal to Q theta I minus 2 omega I GI. Yeah, no, sorry, it's the other way around. Yeah, sorry. It's minus 2 dot okay. This basically comes from this one here when you put it on the other side, okay? Because then you have to basically do a transpose on this one, if you remember. A transpose operation. Come? Però qui c'era sì, infatti c'è un G trasposto. Sì, mi sono dimenticato. Corretto. Sì. Ok?
Here, when we took the derivative of tan theta theta, we separated the derivative between the transpose of G and the normal G. But in the last step, when we took the derivative of on the right part with respect to theta, we only get the derivative of theta.
Here?
Here, in the second step.
Here?
Yes. So
Yeah, because here basically we have the derivation with, so the functional dependence on theta, on the Euler's parameters theta, it's only present here and here, because here we have a dot. You see, a dot in here as well. So here we have a dependence on theta dot inside here, and here of theta dot as well. This basically is constant. So basically our only explicit dependence on the theta here is here and here. All right? And you're left with this one as a result. Okay. All right. Now the last reformulation, then we're done, is basically rewriting this one again as G I transpose applied over I theta theta I and G. This one here. Then we know that, so this one is the first. Then we know that G I applied over G I transposed. If you remember, by the definition of G, this is 4 times, because G is 2 times H, if you remember. So this is 4 times H I over H over bar I transposed. And this is 4 times the identity matrix. Okay. So we pre-multiply, oops, the star by G. Okay, so basically we are pre-multiplying this G. And this basically comes I 4 times theta theta G I theta double dot yes times G I Q theta I minus 2 G I G I dot transposed theta theta I omega I. So we can demonstrate that G I times G I dot transposed is 2 times, if you remember, the skew-symmetric matrix omega I. So denoting as alpha dot I the vector G I over double dot I and F theta I as the force divided by 4. we finally get, and that's the end of it. We have been using, you remember that when we introduce Q matrix is always because we want to denote a vector product. So we can basically restore it. And that's it. So this is the final form, the canonical form of Newton-Euler's equations, in which, as I was mentioning, this one here is Newton, and this one, the second one here, is Euler equation. Okay? So one basically regulates the translation, the other one rules the rotation. And it's written basically in terms of the mass matrix of translation and the inertia tensor. You see? So, yeah. Yeah. I think you've already seen this in other forms, right? Well, it comes from this. And seeing this and seeing how we actually wrote it before, you can see how the code relates to this one. Because the codes use the matrix form that we had seen before. Huh? But they are equivalent. We have just demonstrated it. So when you want to write this, your code writes, well, something which came some slide before. Your code writes this. Okay.
How are constraints represented?
Well, of course, yeah. Of course, then you have to add the constraints to the last one. Okay, of course. Yes, yes. Those are only the equations. Then you have to add the constraints, and the constraints, of course, constitute again a mixture of algebraic and differential equations. So, okay. But here, I know it's a little bit cumbersome and heavy, but this is again eventually why you get this and where it starts from, and how it actually streams from the Lagrange equation. You see, it's just a direct result from Lagrange, which we have basically computed here. Okay, so you start seeing how all these pieces come together. Okay. So next week, what we will see is that in addition to all this complication, because these are quite nonlinear equations, you know that, we will add to the, just to increase the complexity, also deformation phenomena. And on one side, if we said that the modeling of rigid motion basically causes the high nonlinearity of the problem, which is as we see here. The treatment also, the inclusion of deformability, basically cause also what is called the high dimensionality of the problem. What does it mean? It means that you need a lot of variables to represent it. Why? In theory, in an infinite number. Because to model, to correctly represent a body whose every part can move independently from the other, you need an infinite number of parameters, right? So of course you cannot deal with that. So what we do is to basically use some approximation. We'll introduce it on Monday in order to get all these formulation treatable. Eventually, in the last part of the course, we will also see some reducing model techniques, so that you basically, even if you take an approximation, so you don't use the infinite number, of course, of variables, in some cases, you know, if you know what you are interested into your system, in the response of your system, what it does is interest not to you, you can disregard this part that doesn't interest in you in the dynamical response of your system, and therefore still even reduce further the number of parameters which you need to describe it. Okay, you still even reduce the dimensionality of the problem. But this is something that we will see later on. Okay. Okay. That's it.